Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I was discussing definitions of some important terms pertaining to coordination compounds. In that I have discussed coordination entity, central atom or central metal ion, ligands, coordination number, coordination sphere, coordination polyhedron. Now two more terms I will discuss. Then I will start nomenclature of coordination compounds. Then two terms I am going to discuss, that is the Iitjee, oxidation number of central atom. Oxidation number of central atom. Already I have discussed how to find out oxidation state of central metal ion. If complex ion you are knowing, means complex ion suppose has 3 minus or 2 minus, then you can calculate this oxidation state of metal ion in a very easy way, because charge you are knowing, total charge on the complex, how much charge is there, +2, +3, -3, -2, some things are there. If not, then it will be 0. Correct? If no charge is mentioned, it means it is 0. Then easily you can calculate the oxidation state of central metal ion. Then again I am repeating, how will you calculate? Then for that you should know the ligand, what type of ligand is attached. If ligand, as for example, chloride, fluoride, iodide, anything is attached, or nitrate is attached, NO2 is attached, okay, then easily you can determine if you are knowing the charge on the ligand, because formula you know how to calculate the oxidation state. Oxidation state of central metal ion, if you want to know, then suppose you are not knowing, then you consider as a X. And after that, how many ligands are there? Total charge on the ligands. Ligands sometimes may have neutral, no charge on ligand. As for example, NH3, no charge, 0. H2O, no charge, 0. Cyanide, Cn, 1 minus, correct? Chloride, fluoride, bromide, iodide, all have 1 charge, -1, correct? Then how will you calculate? Then suppose you want to know the oxidation state. Suppose it is X plus, suppose 5 H2O is there. 5 H2O is there. Suppose H2O, leave it. 5 chloride ion is there. Then -5, X -5, because you have to add. Then X plus, in bracket, -5. Then remove the bracket, plus, minus, minus. Then X -5 is equal to, suppose it is -1. Then X is equal to +5 -1, means +4. Then in this way, if you are knowing the ligands charge on the ligands, and there is a total on the complex ion, how much charge is there, that is equal to, whatever be, that is equal to that charge. Then easily you can calculate. Then that I am discussing now, oxidation number of central atom. The oxidation number of the central atom is or you can say the oxidation number of the central atom in a complex is defined as the charge it would carry if all the ligands are removed along with electrons pair that are shared with central atom. This is the another way. Just if you want to know oxidation number, then you just consider if all the ligands are removed along with the electron pairs, along with their electron pairs that are shared with central atom. Then obviously all things were removed. Then what was the, you can say, oxidation number? Only that will remain. Oxidation number of central atom only will remain. Then to know that things, this is another method, that if you will ignore, if all the charges are removed along with the electron pairs that are shared with the central atom, that is called oxidation number. The oxidation number is represented by a Roman numeral in parenthesis. That is the way to write, in parenthesis, in Roman numeral, following the name of coordination entity. For example, oxidation number of copper in CuCN whole 4, CuCN whole 4, and out of bracket 3 minus is there. 3 minus is there. Then both method you can apply to calculate that CN4 is there, means minus 4 is there. Minus 4. Then Cu minus 4 is equal to minus 3. Out on the complex, minus 3 minus is there. Then Cu minus 4 is equal to minus 3. Then Cu is equal to how much? Plus 4 minus 3, that is the plus 1. This is the one method. Second method, Cn you forget. Think that Cn is not there. Then Cn charge you remove. Then Cn carry one negative, then 4 negative is there. Cn4 means 4 negative. That you take it away. Take it away. Minus 4 you take it away. And plus 3 was there. Plus 3 was there. Okay, then how much you will get? You will get only plus 1. Same thing will come. Same thing. Better only first method you follow. Okay. Then minus 4, CuCN whole 4, CuCN whole 4, and on the complex 3 minus is there. Then Cu we want to know. Then Cu minus 4 is equal to minus 3. Then C is equal to plus 4 minus 3, that is the plus 1. And it is written as Cu. In parenthesis you write 1 because oxidation state is, or oxidation number is 1. Then Cu, and in bracket, a small bracket, you can write 1. Now another term, actually this is asked in examination, they will ask to calculate oxidation number of the central metal ion. Then easily you can calculate. Now another term is homoleptic and heteroleptic complexes. Homoleptic and heteroleptic complexes. Then now I am telling you what is the homoleptic and what is the heteroleptic complexes. Complexes in which metal is bound to only one kind of donor groups. As for example, CO cobalt NH3 whole 5, cobalt NH3 whole 6. You consider cobalt NH3 whole 6. Outside 3 plus is there. Then here 6 ligands are there. Only one type of ligand is there, NH3, 6. Then this is called homoleptic. Homo means same. Only one type of ligand is there, NH3, 6 NH3. That's why it is called homoleptic. Then complexes in which a metal is bound to only one kind of donor groups. As for example, cobalt NH3 6 and outside 3 plus is there. Then NH3 is 6. Only one type of donor is there, ammonia. Then it is known as homoleptic. Now other way you can understand very easily. Complexes in which a metal is bound to more than one kind of donor groups. More than one kind of donor groups. As for example, cobalt NH3 Cl2. Two types are there, ammonia and chloride. Cobalt NH3 Cl2 and outside 1 plus is there. Then this is the example of heteroleptic. Here two types of donors are there, ammonia and chloride. Okay. Then this is the example of heteroleptic. Now I am going to start nomenclature of coordination compounds. This is very, very important and many question is asked on nomenclature. Just like organic chemistry, you will find in organic chemistry also, already I discussed nomenclature of organic compounds. Same way here it is nomenclature of inorganic compounds. Nomenclature of inorganic compounds. It applies for both organic and inorganic. Then now I am telling for inorganic. Okay. Nomenclature is important in coordination chemistry because of the need to have an unambiguous method of describing formulas and writing systematic names, particularly when dealing with isomers. Correct? Nomenclature is important in coordination chemistry. Why? Because of the need to have an unambiguous method of describing formulas and writing systematic names, particularly when dealing with isomers. Correct this name should be there, systematic names. Correct? And formula, correctly formula, to write correct formula and a systematic name. This is required. Nomenclature is required. Simple meaning of nomenclature is naming of a compound. Naming of compound in a systematic way. The formula and names adopted for coordination entities are based on the recommendation of IUPAC, means International Union of Pure and Applied Chemistry. Now, formula of mononuclear coordination entities. Now I am starting slowly and slowly. Just try to understand. These are very, very important. Formulas of mononuclear coordination entities. Mononuclear, mono means one, single. The formula of a compound is a shorthand tool, you can tell. The formula of a compound is a shorthand tool used to provide basic information about the constitution of the compound in a concise and convenient manner. Mononuclear coordination entities contain a single central metal atom. Single central metal atom. Now I am telling these things, some formulas, some rules I will tell, some rules which are applied while writing the formulas I am telling you now. This will apply for mononuclear coordination entities, means having single central metal atom. First rule, First rule, the central atom is listed first. Okay, this is the easy, very easy. All here in this case, all methods you are knowing. Just I am telling you, might be knowing. First is that central atom is listed first. Second rule, the ligands are then listed in the alphabetical order. Okay, if many ligands are there, 2, 3 are there, then alphabetically you can write. Suppose A will come first, then B, then C, then D, like that, alphabetically. Ligand's name, if it starts with A, that will come first. Then starts with, suppose C is there and then D is there. Then first A, then C, then D, then E, then F, like that. Then the second rule is that the ligands are listed in alphabetical order. The placement of a ligand in the list does not depend on its charge. Okay, this is important. The placement of a ligand in the list does not depend on its charge. Okay, alphabetically you can arrange, you can list it. Now third rule, polydentate ligands are also listed alphabetically. Very good, very important. And this you might be knowing also. If not knowing, then you should know. Polydentate means if ligands may be 2 or 3, you can say atom which can donate electrons. Sometimes maybe 4 also. That's why it is called polydentate ligands. Polydentate ligands are also listed alphabetically. In case of abbreviated ligand, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. Okay, for both alphabetical order is required. The first letter, only one letter, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. Only one letter you have to write, not the full name. Now fourth rule, the formula of the entire coordinate entity, whether charged or not. The formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. Okay, the formula of the entire coordination entity, whether charged or not, is enclosed in a square brackets. When ligands are polyatomic, their formula are enclosed in parentheses. In case of polyatomic, more than one. When ligands are polyatomic, their formulas are enclosed in parentheses. Ligand abbreviation are also enclosed in parentheses. Next rule, fifth, rule 5. There should be no space between the ligands. There should be no space between the ligands and the metal within a coordination sphere. No space. In continuous you can write, there should be no space between the ligands and the metal within a coordination sphere. No space. Now next rule, that is a rule 6. When the formula of a charged coordination entity is to be written without that of the counter ion, when the formula of a charged coordination entity is to be written without that of the counter ion, outside ion, the charge is indicated outside the square brackets as right subscript with the number before the sign. As for example, or many examples already given, cobalt cyanide 6, cobalt Cn whole 6. It is in a bracket, a square bracket, outside 3 minus. 3 minus. Why 3 minus? Now you are understanding. Cn whole 6 is there, means minus 6 is there. And finally minus 3 is there, minus 3 is there. Then if minus 6, if you will take to the right side, then it will become plus 6, plus 6, plus 6, and this 3 minus, then that will be plus 3. Plus 3 is the coordinate this oxidation state of cobalt. Oxidation state of cobalt is plus 3, and Cn is minus 6, 6 Cn, minus 6, and finally minus 3. Then actually on complex, out of complex means out of a bracket, finally is written. Finally 3 means coordinates oxidation number of metal plus oxidation number of ligand. What will come? That is that charge will come on the complex ion. Addition of both. Cobalt, as for example, cobalt is 3. Cobalt oxidation state is 3. Then 3 and plus cyanide is 6. Cyanide is plus 6 cyanide. Then each cyanide is minus 1. Then now it becomes cobalt minus 6. That is equal to 3 minus. Then obviously 3 minus 6. 3 minus 6 is equal to minus 3. Hence addition of both oxidation state of metal ion plus oxidation state of ligand, that is equal to charge on the central ion. Charge on the central ion means out of the bracket, okay, or on the bracket, square bracket. Another example I am telling you, that chromium H2O whole 6. Chromium H2O whole 6. Then H2O is neutral. H2O is a neutral, no charge. Only it will oxygen has a lone pair of electron that it will give to the d orbitals. But charge is no charge, 0. Then chromium has 3 oxidation state. Then 3 plus 0, that is equal to 3 only. 3 plus 0, that is equal to plus 3. That's why here in this complex, on the complex ion, 3 plus is there. 3 plus is there. I think you have understood how charge is written outside. And last point is there. Last rule, the charge of the cations. The charge of the cation is balanced by the charge of the anion. Means charge of the cation, suppose complex is cation. Complex is cation means plus charge. Then same number of negative signs should come in the form of anion. Then cation is balanced by charge of the anion. The charge of the cation, suppose plus 3 charge is there on cation. Then on anion minus 3 should be there, means total minus 3 should be there. Then charge of the cation is balanced by the charge of the anions. Okay. Now I am coming to the distance. Actually, this 2004 IUPAC draft, new things I am telling you, 2004 you can say recommendation of IUPAC. The 2004 IUPAC draft recommends that ligands will be sorted alphabetically irrespective of charge. Irrespective of charge. Alphabetic term has come in 2004 according to IUPAC. IUPAC has given importance for alphabetically arrangement, not by charge, irrespective of charge. Now I am telling you about the naming of mononuclear coordination compounds. That was the entities what I discussed. Mononuclear coordination entities means in bracket, square bracket rule I have discussed. That will appear only, this all rules will apply only in bracket, in a square bracket, only for entities or complex ion. Now I am telling for entire compound. Naming of mononuclear coordination compounds means here if you will consider cation and anion both, means entity means complex ion and for counter ion, for both will work here. Okay, complete coordination compounds. The names of coordination compounds are derived by following the principles of additive nomenclature. Principles of additive nomenclature. Thus, the groups that surround the central atom must be identified in the name. The groups that surround the central atom must be identified in the name. They are listed as prefixes to the name of the central atom along with any appropriate multipliers. Now I am telling the rules. Some rules are there to name the coordination compound. Okay, then one by one I will tell. Okay, there this 7 rules are there. 7 rules I will tell. Listen carefully. All rules will be used. Okay, that's why just listen carefully. First rule is that the cation is named first in both positively or negatively charged coordination entities. Means complex ion is either positive or negative, whatever be. Complex ion may be positive, complex ion may be negative. Means entity may be negative, entity may be positive. The cation is named first, whatever be, the cation is named first in both positively and negatively charged coordination entities. If both are there, then first you write the name of cation, not the anion. First to write the cation, positively charged. Second rule, the ligands are named. The ligands are named in alphabetical order before the name of the central atom. Central atom or ion. Okay, very, very important. The ligands are named in an alphabetical order before the name of the central atom. This procedure is reversed from writing formula. Okay, this procedure is reversed from writing formula. First you write central atom, always remember, and after that this ligand will start. The ligands are named in an alphabetical order before the name of the central atom. Now third rule, name of the anionic ligands. Suppose both these things, cation is also complex ion and anion is also complex ion. Then in that situation I am telling you, suppose anion is a complex ion, suppose. Then names of the anionic ligands ends in O. Remember it. Dash and O you write. One dash, a small dash, and O you write and the end of the ligands. Then third rule is there. Name the anionic ligands. Names of the anionic ligand. Anionic ligands I am talking about, not the cationic. Names of anionic ligands end in O. Dash, a small dash, and O. Those of the neutral and cationic. Okay. Names of the anionic ligands end in O, dash, small dash and O. Those of neutral and cationic ligands are the same, except for aqua for H2O. For H2O you can write aqua, otherwise name you can write. Okay, for neutral and cation ligands are the same. Neutral and cationic ligands are the same, their name will be the same. And only for aqua you can write H2O, and for NH3 you can write amine. And for carbonyl, for CO you can write carbonyl, and for NO you can write nitrosyl. This you remember. Names of the anionic ligands end in O, correct? Those of neutral and cationic ligands are the same, except aqua for H2O. These are the exception. Aqua for the H2O you can write aqua. For NH3 you can write amine. For ammonia you can write amine. For carbon monoxide you can write carbonyl. For NO, nitric oxide, you can write nitrosyl. Okay. These are placed within enclosing marks. These are placed within the enclosing marks in a small bracket. Now fourth rule. Prefixes mono, di, tri, etc. are used to indicate the number of the individual ligands in the coordination entities. Suppose 3Cl is there, then you can use the word trichloride. If 2 are there, then dichloride. If 3 are there, then trichloride. Okay, like that way, prefixes, only one is there, then you can write mono. Then prefixes mono, di, tri, etc. are used to indicate the number of the individual ligands in the coordination entity, means complex ion. When the names of the ligands include a numerical prefix, then the terms bis, tris, tetra, kis are used. You remember. When the names of the ligands include a numerical prefixes, then the term bis means for 2, tris for the 3, and tetra, kis for the 4 are used. The ligands to which they refer being placed in the parenthesis, for which you are writing bis, tris and tetra, kis, that ligand you write in a bracket, parenthesis. For example, nickel, NiCl2, nickel, Cl2, nickel, NiCl2, and PPH health, PPH3 whole 2. Actually, central metal is nickel. 2 chlorine is attached, Cl3l. After that, PPH3, 2 PPH3 is attached, PPH3 whole 2. PPH3 whole 2 means 2 PPH3 is attached. Then how will you give the name? Then this you have to name like I am telling you. 2 chlorine is there, means 2 chloride ion is there, then you can write dichloro. O you are writing dichloro. Okay, and for PPH3, 2 PPH3 is there, then PPH 2 PPH is there, PPH3 first to understand, that is in 2 number. Then dichloro, and because PPH3 is in 2 number, whole 2 is there, that's why you will use the term bis, BIS, because PPH3 is in 2 number. then bis you have used. And what is actually PPH3? Then PPH3. Then for the 3 you will use tri. PPH3, for the 3 you will use tri. And PH3, that is the phenyl. Phenyl. Then you can write triphenyl. And one more P is there, phosphine. That is for phosphine. Why it is written like that? PPH3 means with the P. PH3 gas is there. PH3 gas is there. Phosphine gas. 3H is there. Then now this 3H is removed by PH, phosphine. 3PH, 3 benzene ring has attached. 3 benzene rings. That is shortcut phenyl group, what we are telling. PH. That's why one P is telling about the phosphine. PH3, 3H removed. And in each H, one benzene ring came. Benzene ring. That what we are telling, what we are telling is this thing, phenyl group, also phenyl group. Then triphenyl phosphine. Triphenyl phosphine. Nickel 2. Nickel, because oxidation state is 2, in bracket you can write in Roman 2. Nickel 2. Then see how you have written name of this complex. This question may be asked in examination. NiCl2 PPH3 whole 2. Then first you have used the C, chloro. 2 are there, the di, and P you are not using. Alphabetically you have to arrange. Then first C you have to write, means dichloro, and after that PPH3 whole 2 is there. Then for that you have used the word bis, BIS, and in bracket this bis you have used for what? This bis you have used for what? That you write in bracket. That you have written for triphenyl phosphine. And the end you write nickel third. Nickel third. Okay. Now here I am talking about the next rule. Rule 5th. Oxidation state of the metal in cation. Already I discussed. Same way here. Oxidation state of the metal in cation, anion, or neutral coordination entity is indicated by Roman numeral in parenthesis. Already I told. Now next rule 6. Rule 6. If the complex ion is a cation, the metal is named same as the element. If the complex ion is a cation, remember plus, okay, cation, then in that situation the metal is named same as the element. For example, cobalt in a complex cation. Suppose cobalt is there in a complex cation, cobalt is there, then it is called cobalt, and platinum is called platinum. If in cation, if a complex ion is cation and cobalt is there, then you write only cobalt. Cation is called cobalt. And suppose platinum is there, then platinum is called platinum. If the complex is anion, now think for the anion. If the complex ion is anion, the names of the metal ends with suffix ate, 8, eaten, that 8, ate, 8, and will be 8. If the complex ion is an anion, this is important. The name of the metal ends with the suffix 8, ate. Okay, for example, cobalt in a complex anion. Suppose cobalt is in a complex anion. What I discussed in the beginning, that was in cation. Now suppose cobalt is in anion complex, negative. Then how will you tell about this cobalt? Then for example, cobalt in a complex anion. Suppose anion is cobalt SCN whole 4. Outside 2 minus is there. That's why it is anion. Then this will be called cobaltate. Cobaltate, not cobalt. Cobaltate. Then in anion, you are telling cobaltate. For some metals, the Latin names are used in the complex anion. Okay. For some metals, the Latin names are used in the complex anions. Example, for ferrous, Fe, you will write ferrate. Ferrate, here also ATE is coming, ferrate. Now, just come to the next rule. Rule 7th. The neutral complex, no charge is there. Complex is there, no charge. Neither negative nor positive. Neither cation nor anion. The neutral complex molecule is named similar to that of the complex cation. Simple, we will tell just like a name of complex cation. Now examples. This nomenclature examples I will tell you. Now suppose these things, chromium Cr-NH3 whole 3, H2O whole 3, and outside Cl3 is there. Already it is a compound, neutral. You are not talking about complex ion. It is now compound. Okay, because that charge is neutralized by chloride ion. Outside counter ion is Cl3, because this was Cr-NH3 whole 3 H2O whole 3 in bracket. It was actually plus 3, but now it is neutralized by 3 chloride ion. Hence finally compound is 0. Finally it is neutralized, becomes 0. Then how will you do nomenclature? Then again I am telling the name of the compound, Cr-NH3 whole 3 H2O whole 3, and outside Cl3 is there. Then you will write tri, because Cr-NH3 whole 3 is there. Then you can write triamine. NH3 whole 3 is there. Then write triamine. After that 3H2O is there. Then again you write triaqua. For the H2O you can use the term aqua. Then triamine. Triaqua. Now chromium you have to write chromium. Then you write chromium, because it is a cation, part of the cation. Then first cation one should write first cation. That's why you are writing in cation inside the cation 3 ligand you have written for ammonia, 3 ligand you have written this H2O, triamine, triaqua. Now cation you are writing. Okay, just like it is your title. Suppose your name is since some title, your family title is there. Suppose Singh, Sunil Singh. Then Singh you can write first, and then your main name will come. Or your father's name, grandfather names also you can write. In South India it is popular. Okay, grandfather, father's name, then son name, like that way. But whatever you want, before your name you can write some things. Then same situation is there. Cation you are writing. Main cation. But before cation, your subtitle you are writing. Then here triamine. Here you are writing in a alphabetical. Amine means A. Okay. Then triamine. Again H2O. H is coming. H2O. water you can tell W. But anyhow, aqua you are writing with aqua. Then after triamine you write tri-aqua. And then chromium you are writing. Chromium third, because oxidation state is third. Okay. Then third, and then you write chloride. Then triamine, tri-aqua, chromium third, chloride. Third you are writing in bracket. Three you have written in numerals, in Roman numerals. Now, here I am giving another example. Cobalt. Now actually ligand is two. They have two donor. Monoligand, didentate ligand. This is a didentate ligand. CH2 is in the middle, and both end NH2 is attached. That is 1,2-diamine. 1,2-diamine is attached with cobalt. This is actually central metal ion. This is the complex ion, cobalt with the cobalt, 1,2-diamine is attached with the cobalt. And there are these ethane 1,2-diamine is in 3 molecule. Ethane 1,2-diamine, again ethane 1,2-diamine, again ethane 1,2-diamine. Then 3 molecules are attached with cobalt. Okay. And now here you can see not 3, 2 is attached. Cobalt 1,2-diamine, ethane 1,2-diamine, not only 3, whole 3 is there, whole 3. Then 3 are attached, correct? Then here what you will find that here on the complex 2 negative charges there, 2 positive charges there. Okay, this actually charge here is somewhat difficult example is there. This example actually this complete complex cobalt 1,2-diamine, that is in 3 number. Okay, 3 number first things, and again this 3 number, first is 3 number, 1,2-diamine, again 1,2-diamine, again 1,2-diamine, 3 number. Again actually this cobalt, this complex ion is 2 complex ion is there. What I told you, cobalt, ethane 1,2-diamine, already 3 times it is attached. That is the one complex ion. That is one complex, only one complex. But here in this example you are considering 2 complex having the same, means COH2N, CH2, NH2N. Okay, with one cobalt 3 times this is attached, correct? That is the one complex. Now one same complex is again there, means 2 times this complex is there. 2 times, same complex 2 times, means having 3 moles of 1,2-diamine attached with cobalt, correct? Then whole complex you can write like that, 2 times you can write. That is the CO NH2, CH2, NH2, whole 3 you have written, correct? That is for one complex. But there is a 2 complex. Then in whole complex you write in a big bracket, and outside you write 2. outside you write 2. Okay. Then charge, what will be the charge? What will be the charge in the complex? Then here actually +3. Cobalt has +3 oxidation state, but 2 cobalts are there. 2 cobalts are there having 1,2-diamine. Then total 6 charge is there. Total 6 charge. +3, 6 charge. Then to neutralize this charge, this 6 charge, 6 negative should come. That's why in the complex compound, SO4 whole 3 is written. Just like, then you know that H2SO4, SO4 is 2 negative. SO4 is 2 negative. Then here to neutralize 6 positive, 6 negative is required. That's why SO4 whole 3 is written. Or one should write SO4 whole 3. Then complete coordination number will be neutral. Okay. Then now how will you write these things? Name of the compound. How will you do nomenclature? Then now nomenclature I am telling you. Then here, because 1,2-diamine is 3 times. Then you write tris. Then this tris you are writing for the ethane 1,2-diamine. Then now 1 is over. After that nothing is there, cobalt is there. Only ethane 1,2-diamine is there, but only these things are there 3 times it is attached with the cobalt. That's why you have written tris, and in bracket you write ethane 1,2-diamine. And because it is the cation, then cation you should write first. Then in that cation now title you have written, now your name you are writing. Now cobalt third you write because oxidation state is 3. And in the end it is a sulfate SO4 whole 3. Then you write only sulfate. Now one more example I am telling you. Actually this type of question will be asked. It is fit for the medical or advanced, IIT advanced. Now third example I am telling you. AgNH3 whole 2 and other means this is actually cation, and other anion is also AgCN whole 2. AgNH3 whole 2, it is a complex ion, cation complex ion, and anion complex ion is AgCN whole 2. Both are Ag. Only difference that with first NH3 whole 2 is there, and with second Cn whole 2 is there. Very good question. Very good complex. This is also fit for the all examination. AgNH3 whole 2, and there is a one complex and other complex. There is a complex cation, and complex anion is AgCN whole 2. Then how will you write? I will do nomenclature. Then very easy. First cation you do. First you do for cation AgNH3 whole 2. Then for the 2 you will write di. NH3 is there. Then amine you write. Diamine. After that you are writing cation. Means title you have written, your name you are writing silver 1. Because here silver oxidation state is 1. Okay, 1. That's why you have written silver 1. Now silver 1 means here NH3 is a neutral, you know. Then finally on cation it will be 1 only, because silver has 1 oxidation state. Hence it will be only +1 on the cation, only 1 plus. And now come to the anion. AgCN whole 2 minus. Then again Ag oxidation state is +1, you know. Cyanide is -2. Then finally it will be -1. Then anion is -1, cation is +1. Then charge is fully neutralized, 0. Then now for this anion, how will you do these things? Nomenclature. Then AgCN whole 2 is there. Then dicyano. I told you in case of anion, two rule is important. For ligand O you add, and for the metal ATE. Always remember, for the ligand in the case of anion, for the ligand O you add and the end, and for the metal ATE. Then now here for the anion you can write AgCN whole 2 dicyano, and for silver arginate. Argin means silver. Arginate, ATE, and at the end you write arginate, argent you write ARGENT, argent, ATE, argentate. Correct? Then now I have told about the you can say different rules of nomenclature. Okay. Today I am stopping only here. Next class I will continue with isomerism in coordination compounds. Thank you.